What's up, my stat stars? Michael Princhak here for the Unit 2 summary review video over exploring two-variable data. In this video, we're going to cover all the major concepts, all the major themes from Unit 2. But before we begin, I want to mention two really important things. First, this is just a review video. I'm not going to go over all the teeny tiny details, formulas, and definitions that you may have learned, because that's what you were supposed to learn when you were in class. We're just going to cover the big ideas, the big concepts that are going to allow you to perform really well on the AP Stats test and on your unit test. The second thing I have is an awesome study guide that corresponds with the material in this video. So please get out that study guide. Feel free to pause the video, fill it out as need be, or you can watch the full video and fill it out at the end, whatever you want. But I also have the answer key. How do you access that study guide and answer key? Please visit the video link below, and you will have access to the ultimate review packet. There's a free trial. You should get a lot of stuff for free right now. It contains lots of great stuff, practice sheets, study guides, everything you need to know and do to make sure you are ready, not just for your unit test, but for the AP Stats test in May. All right, let's get ready to dive right into Unit 2. Unit 2 covers exploring two-variable data. That's taking one set of data and collecting two variables from it. We then analyze those two variables and how they possibly are related to each other. Again, one set of data, two variables collected from it. Maybe that's one sample of frogs and their lengths and their weights were measured. Or maybe that's one sample of hospital patients and their ages and how long they stay at the hospital was recorded. Maybe it's one sample of kids and we track their age and their TV watching habits. The idea is one sample with two variables measured from it. But the major theme here is discovering how those two variables are related or associated. So maybe we want to look at how the lengths of a frog are related to the weights of the frogs, or maybe we want to look at how the age of a patient is related to how long they stay at the hospital if they have to go. Or lastly, maybe we want to look at how the age of a child has something to do with their TV watching habits. It's all about discovering the relationship between those two variables that we measured. The unit is broken down into analyzing two categorical variables and how they are related. And then the second part of the unit is looking at how two quantitative variables are related. In each of these major sections, looking at categorical data or looking at quantitative data, we first take a look at graphs, statistics from the data, but then we really dive into how can we determine that those two variables are related. Now, maybe we see patterns in our data, maybe we don't, and those patterns that we see might be random and they might not, but they're going to provide us critical information to help us determine if those two variables have any type of relationship whatsoever. First, let's start with analyzing one set of data where we collect two categorical variables from that set of data. The best way to organize and understand our data is with what's called a two-way table. Let's take a look at one now. Here's a two-way table where we looked at a sample of students and we asked them two questions. First, how did you get to school? What was your mode of transportation? And second, were you tardy at least once in the last week? From a table like this, we could calculate some sample statistics. Now, why are they called sample statistics? Well, because they come from a sample. Remember, statistics is the word that we use for any information that is taken from a sample. We have several different types of statistics that we can gather from one of these two-way tables for categorical variables. First, what we have are what are called marginal relative frequencies. Here, we're looking at the values that are in the totals. That's why it's called marginal, because the totals are in the margins of the table. We can either look at the proportion of all the kids that were tardy at least once that week, or the proportion of kids that were not tardy at least once that week. We could also look at the margins for the different types of transportation, like the proportion of kids that rode the bus, the proportion of kids that walk to school, the proportion of kids that drive themselves to school, or the proportion of kids that get a ride from their parent to school. But again, we calculate these values from the totals by dividing it by the grand total, hence the marginal relative distributions. Next up, we have what's called joint relative frequencies. When we say the word joint, we basically mean the word and. So we're combining any two of the categories together. For example, we could look at the proportion of kids that were tardy and rode the bus. Or we could look at the proportion of kids that walked to school and drive themselves to school. For a joint relative frequency, we're looking at a specific value that matches for those two variables in the table, and again, dividing by the grand total. Lastly, we have conditional relative frequencies. These are a little bit more confusing, but once you get the hang of it, it's really simple. The idea is there's a condition attached, and when there's a condition attached, it changes the value in the denominator. For example, you'll see, given a student is tardy, what proportion of them ride the bus to school? So the condition is that it's given that they were tardy. That means our denominator is only limited to looking at the kids that were tardy because it was given, right? There was a condition attached. We know that the student that we're talking about was tardy to school. So our denominator becomes much, much smaller because we're only looking at those students that were tardy. And of those tardy students, how many of them rode the bus to school? So we take how many rode the bus to school and were tardy, and we divide it by the total that were tardy to get our conditional relative frequency. Another example we see here is, given that they walk to school, what proportion of them are tardy? This time the condition, what is given, is that they walk to school. Once again, that limits our denominator to only looking at kids that walk to school, because that's the condition, that's what we know. The numerator is both walking to school and tardy. So take that value divided by the total of kids that walk to school, and you'll have your conditional relative frequency. Hopefully that makes a lot of sense. For all three of those statistics that we looked at, marginal, joint, and conditional, notice that we looked at the relative frequencies. We didn't look at just the counts or how many. Why is that? Because when you have unequal sample sizes, or again, a different amount of kids that walk to school, different amount of kids that take the bus to school, different amount of kids are tardy, different amount of kids that are not tardy, it makes more sense to compare proportions or percentages or what's relative to the whole. If we just look at counts, it's not really fair because some, more kids might take the bus to school, less kids might walk to school. So just looking at counts isn't really a fair comparison. But if we're going to compare probabilities and proportions within these tables, it makes way more sense to look at relative frequencies, which are proportion-based. Two-way tables can also be turned into some pretty sweet graphs called segmented bar graphs. Here we see a segmented bar graph where we've broken down the bars by mode of transportation. And then within each mode of transportation, we're separating the proportion of kids that were tardy and the proportion of kids that were not tardy in that mode. So basically, we're looking at conditional relative frequencies here, because the first bar is only for those kids that ride the bus. And of those kids, what proportion are tardy, what proportion are not. So we can see the breakdown for each mode of transportation. We could also switch that around and now have each bar representing the proportion of kids that are tardy and the kids that are not tardy. So the first bar we see here is all the kids that were tardy, and then the breakdown of what proportion of them ride the bus, what proportion of them walk to school, what proportion of them drive to school, and what proportion of them get a ride from their parent. And then we also see the same thing in the bar that's marked the total kids that were not tardy. Again, each segment is the proportion of the different modes of transportation. So we could switch it up and it's all provided the same amount of information. It's really just a matter of what the condition is. Is the condition the mode of transportation, or is the condition being tardy or not? That would determine how you create the segmented bar graph. But segmented bar graphs show the proportions within each of those conditions. They make for great ways to display the data and really understand what's going on within the data. Now, the really important thing we want to do here is determine if there is any type of an association or relationship between these variables of mode of transportation and being tardy or not. Now, to do this, we really have to take a look at the marginal relative frequencies versus the conditional relative frequencies. Now, please note, when we say that there is an association between two variables, we mean that they are not independent. An association means that one variable has something to do with the other variable and vice versa. If two variables are independent, they actually have no association whatsoever, which means one variable does not impact the other. Let's dive into this example to talk about if there is an association or not. Here's how we can actually explore the relationship between these two quantitative variables. So first, we want to take a look at the marginal relative frequency. For example, what proportion were tardy at least once? So here we see the marginal, again, 65 out of 188 kids, or about 34.6% of all the students surveyed were tardy at least once. Then what we want to do is we want to compare to that the conditional relative frequencies. So meaning if we only look at the kids that rode the bus, so of the 35 kids that rode their bus, 12 were tardy, that's about 34%. Of the 29 kids that went for their parents to school, 10 were tardy, it's about 34% as well. Of the kids that drove themselves to school, it's about 31 out of 90, again, also about 34%. And then finally, of the 34 kids that walked to school, we saw about 12 that were tardy, or about 35%. So what we're noticing is that, we start off with that marginal, about 34% of kids are tardy to school at least once during the week. But notice that if you ride the bus, about 34% tardy. If you drive to school with a parent, about 34% tardy. If you drive yourself to school, about 34% tardy. And if you walk to school, pretty darn close to about 34% are tardy. This is a sign of no association, because what we're showing here is that, again, start off with that marginal. 34% of kids are tardy. However, if you arrived to school by bus, it didn't go up, it didn't go down, it stayed about 34%. If you drove with a parent, it didn't go up, it didn't go down, it stayed about 34%. If you drove yourself, it did not go up, it did not go down, it stayed at about 34%. Yeah, walking, I know, is a teeny bit more, it's about 35.3%, but again, it's really, really close to 34%. So what we're seeing is that the added conditions of how you got to school did not make it any more or less likely for you to be tardy. It's all around 34-ish%. This isn't a sign of an association. When you attach a condition to a question and it doesn't change the marginal relative frequency, well then there's no association. Clearly, how you arrive to school does not make you any more likely or less likely to be tardy. Now, that's in stark contrast to looking at this example. So here I'm using the same concept, the same idea, being tardy, yes or no, and how you got to school, but I changed the numbers a little bit. But first, I want you to notice that the grand totals are all the same. It's the numbers within the table that I made different. Now, in this example, we're going to see that there is a clear association. For example, once again, we start off with the marginal relative frequency, where we see about 65 out of 188 kids were tardy to school, again about that 34%. But this time, when we look at the kids that rode the bus, of the 35 kids that rode the bus, only 4 were tardy. Wow, it dropped to 11%. So again, something about riding the bus made you less likely, or there's less of a chance that you are tardy. If you drove with a parent, 5 out of those 29 kids were tardy, about 17%, also a little bit less than that marginal value. And if you drove yourself, of the 90 kids that drove themselves, 48 were tardy. That is now up to 53%. So we see that if you drive yourself to school, you are much more likely to be tardy. And then lastly, of the kids that walked to school, 8 were tardy, and that's at about 24%. So here we're seeing very different numbers. The marginal relative frequency, that 34% number, is not matching up with the conditionals. That is a sign of an association, because this is showing that when you add that added condition of, hey, I drive, I go in the bus to get to school, it made me less likely to be tardy. And if I drive myself to school, it made me much more likely to be tardy. This is where we see that there is an association, because those conditions change the probabilities or change the proportions. We can also see this concept of an association or not in the segmented bar graphs. Here's the segmented bar graphs for our data that showed no association. Notice, no matter how you get to school, bus, parent, self, or walk, about 34%, that's the bluish, that are tardy, and about 66%, that's the purple, that are not tardy. Again, showing that it doesn't change. Driving a bus, going with your parents, driving yourself, doesn't change those proportions, which means no association. Where here is the segmented bar graphs for the example where there is an association. We see that when you drive yourself to school, there is a change, in a noticeable change, the proportion of kids that are tardy versus the proportion of kids that are not tardy. So we don't see the exact same numbers across the board. When you see the exact same numbers across the board, 34, 34, 34, 34%, that's a sign of no association. When you see a change of those conditional relative frequencies, that's a sign that there is an association. So make sure you know how to establish these concepts by looking at the segmented bar graphs or by looking at the two-way tables and then writing up a nice explanation of that. Now, from this section over analyzing two categorical variables measured from one set of data, what are some big things that are going to come up on your exam or on the AP exam? Well, the major things we're looking at are just calculating some of those different statistics that I mentioned. Can you calculate marginal distributions, joint distributions, or conditional distributions? Just being able to find those values in a two-way table is really, really simple and really, really easy to do, but it's definitely going to be asked of you. The second thing you're going to have to be able to do is answer that question, is there an association from looking at either a two-way table or looking at a segmented bar graph? That's a big concept, a big idea that is definitely going to come up on the AP exam for sure. The second major theme coming out of Unit 2 is analyzing two quantitative variables measured from the same set of data. Again, this would be like taking a sample of frogs and looking at the lengths of the frogs, that's a quantitative variable, and the weights of the frogs, that's also a quantitative variable, again, values that are measurable and numerical based. Now, when you're analyzing the relationship between two quantitative variables, absolutely nothing beats a scatter plot. When you are trying to create a scatter plot, both variables must be quantitative. Trying to make a scatter plot with categorical variables would be like me trying to make a mullet look good. When creating a scatter plot, the one thing that matters most is that both variables must be quantitative. You cannot make a scatter plot with one or two variables being categorical. The variable on the x-axis is known as the explanatory variable, and the variable on the y-axis is known as the response variable. The explanatory variable is the variable whose values try to predict or explain the corresponding values for the response variable. When you are given or when you create a scatter plot, you're oftentimes going to be asked to describe what you see. In that description, you want to make sure you mention four really important things: the direction, the form, the strength, and any unusual features that you may see in that scatter plot. I also like to add a fifth component to that description, and that is simply describing what you see in context to the problem, meaning using the variables and the units that are present in that specific problem. Let's dive into each of those four components in specifics. First, when we talk about direction, we talk about positive or negative. The explanatory variable on the x-axis is always increasing. If the response variable is also increasing, we say that that's a positive direction. If the response variable is decreasing as the explanatory variable increases, that is said to be a negative direction. Next up, we have the form. The form is basically what shape or what form you see those dots on the scatter plot creating. A very common form that we see is linear. We could also see a giant curve, whether it be logarithmic curve, an exponential curve. We could also see a parabolic curve, which you guys know what a parabolic curve looks like. It goes up and then back down. Now, you're never going to see a perfect relationship in the real world. So don't ever expect to see a perfect curve or a perfect straight line. There's always going to be a little bit of scatter to it, which brings in our third component of strength. The strength of the scatter plot is how closely the points create the form that you see. If they really clearly make a line, then you're going to say it's pretty strong or very strong. Same thing if it makes a very nice, perfect curve, you're going to say it's a pretty strong relationship. The last piece is unusual features. Here we're talking about maybe you see a big gap, maybe there's a bunch of points at the bottom, a bunch of points at the top, and a big gap in between, or maybe half of it's linear and the other half is curved. You know, an unusual features is really something that doesn't always occur, and you don't always have to mention it, especially if there isn't anything unusual about it. But oftentimes, if you see anything unusual going on in your graph, like clusters here and clusters there, and maybe each cluster is doing something different in terms of one cluster is being positive, another cluster is being negative, whatever, you want to make sure you mention it. But lastly, don't forget about that fifth component that I mentioned, simply talking about what you see in context. Oh, hey, I noticed that as the length of a frog goes up, there's a tendency for that frog to weigh more. Again, I'm basically saying that it's positive, but I'm using it in a way that is using the words of the problem, which is what we mean when we say in context. Now, direction's pretty easy to see, positive or negative, and form's usually pretty easy to see as well, but strength is one of those things that's a little bit tricky. In the beginning, we're just kind of vague, like strong, very strong, weak, but we actually want to create a very more specific way to analyze the strength relationship, and we do that with actually something called the correlation coefficient. This is a numerical value that actually tells you how strong a relationship is. But there's a couple really important rules. The correlation coefficient is a numerical value that we call R. Why R? Well, there's two R's in correlation, is all I could come up with. But the idea is that it measures the direction, it quantifies the strength of a linear relationship between two quantitative variables. So the rules are that you would only ever even dream of using R correlation to measure strength if your data is linear. So if you see a giant curve in your data, don't ever even think about using correlation. It's only for linear data. And the two variables absolutely positively must be quantitative. You can never even mention correlation with one or both of your variables is categorical. It's actually a very common mistake that you might see all over the place. You'll see people that totally misuse the word correlation. They'll say, oh, there's a correlation between somebody's height and their eye color. That's an impossibility because eye color is a categorical variable. Now, there's a couple key aspects. First, I mentioned that it gives the direction. That's because correlation can be either positive or negative. So if it's positive, the direction is positive. If the negative, then the direction is negative. That's pretty straightforward. Now, how does it quantify strength? Well, that's because correlation is on a scale from -1 to 1, including -1 and 1. Anything closer to 1 or closer to -1 is actually stronger. So the closer we get to a value of 1, the stronger the relationship in a positive direction. The closer we get to -1, the stronger the relationship in a negative direction. If your data is, which again is very unlikely in the real world, but if your data is a perfect straight line that is going up, it would have a correlation of 1. If it's a perfect straight line that's going down, it would have a correlation of -1. But for anything that has a little bit of scatter to it, it's going to be somewhere in between -1 and 1. Now, the closer the correlation value gets to 0, the weaker the relationship is. Anything from -0.5 to +0.5 is probably on the weaker side. We like to see strength or using that word strong when we are above +0.5 or below -0.5. Now, the other cool thing about correlation is that it has no units. So don't ever put units on it either. It's not like the units are inches or feet or miles or anything like that. It's just a numerical value that tells you how strong that relationship is between two quantitative variables. But I have to mention this one more time. They need to be linear. Now, there is a pretty complicated formula to finding correlation, which I'm not even going to waste your time showing because you're never going to use it. The correlation will either be given to you or you could easily calculate it on a calculator. Let's take a look at some examples of scatter plots and the correlation that measures the strength of them. Now, here we see a scatter plot looking at the weight of a sample of people and the number of steps they take per day. So maybe we took a large sample of people, we asked them what their weight was, then we had them use some type of tracker to see how many steps they take per day. Here we see a linear relationship, but we almost see a horizontal line. We don't see anything major happening. In fact, we don't even see positive or negative. If anything, it might be slightly positive. That's actually evident through the correlation, which is 0.062. So again, it's positive, so it does show that if you are heavier, the number of steps that you take per day goes up, but it's not a very strong relationship at all. In fact, it's extremely, extremely weak because it's close to 0. And that actually makes sense because the fact that we see a horizontal line here means that as the weight goes up, the number of steps you take doesn't go up or down, showing that they're not related whatsoever. Here is another scatter plot looking at several houses, and we're looking at the size of the house in square feet and the price of the house in thousands of dollars. Now here we see a very positive linear pattern, and corresponding such, it has a very strong correlation. Notice its correlation value is first positive because the bigger the house, the more expensive it costs, but it's also very, very close to 1, which shows that it is extremely, extremely strong because those dots are clearly forming a positive linear relationship. Now, here we see another scatter plot looking at the IQ of a sample of people and how long it takes them to complete an online dissection of a frog. So basically, here we had a bunch of high school students. We measured their IQ and how long it took them to complete this online dissection. Now, we definitely see a negative relationship. We definitely see that the smarter the kids are, the faster or the lower the time it took them. But it's not perfect. It's not extremely strong. We definitely see quite a bit of scatter. And that is why we see a correlation value of -0.621. Negative because it's clearly going down. That's the direction. But 0.62 it's on the stronger-ish side, but it's approaching weak. And again, we see that because of the fact that there is a lot of scatter in this scatter plot. But we definitely see that negative association here. Finally, here we're looking at a sample of trees where we're looking at the diameter of each tree measured in inches and the height of each tree measured in feet. Now here we might want to take note that we see kind of two clusters. We see this cluster down here of some smaller trees, and then we see this larger cluster data up here. But if we're looking at the overall pattern of all the data, it does appear to be positive. The larger the diameter of the tree, the more likely it's going to be a taller tree. That kind of makes sense. And we see the correlation here is 0.773, which again is positive and pretty strong. It's not, close to 1 like a 0.9, which would be very strong, but it's definitely somewhat strong. Now, the other thing I want to make sure I notice or tell you guys about in all of the scatter plots we looked at is none of them were perfect straight lines. A perfect straight line is very rare to see. So please make sure that when we look at a scatter plot, we're not looking for perfect linear. We're looking for something that is, approximately linear or somewhat straight, meaning that it's somewhat linear. It's not perfect, but in all three of these examples, it's somewhat forming a line. It's definitely not forming a clear curve, and that's when we're going to definitely want to use correlation to measure the strength. One last final note here. A perceived or real relationship between two quantitative variables does not mean that one variable causes the other variable to change or occur. This is really important for you to understand that even if you have a very strong correlation, that does not imply causation between the two variables. The next step in the analysis of two quantitative variables is to create a regression model. A regression model is used to take values of the explanatory x variable and make predictions for the response or y variable. Now, statisticians love linear data. So if we have a scatter plot and we determine that its form is linear and we're using correlation because we would only ever use correlation if the form is linear, then what we could create is what we call a linear regression model. You guys have probably heard this before. It's called the line of best fit, but in statistics class, we called the linear regression model. Here is that linear regression model. Y hat equals A plus BX. Now, A is the y-intercept of the linear equation, and B is the slope of the linear equation. X is obviously the explanatory variable that we're going to use to try to make a prediction for the y variable. Now, why do we have that little hat? And yeah, it is called a hat on that y. That is to denote that it's not an actual y value, it's merely a predicted y value. This is exactly what linear regression models do. They take explanatory values and they make a prediction for the response. Here's a specific example of a linear regression model. First, we see the scatter plot looking at the IQs of students and how long it took them to complete that online dissection. And we see our linear regression model, aka the line of best fit, going through the data. Now, first, here is the actual specific equation for our linear regression model. Now, we see our y-intercept. That is going to be the 93.759. That's our A value. And then we see our slope here. That's our B value of negative 0.0635. X is, of course, the explanatory variable. In this situation, that is their IQ. And Y hat, the predicted time it would take them to complete the dissection. So in this first example here, we see that we wanted to predict how long it would take a student to complete the online dissection with a IQ of 115. So that's exactly what a linear regression model does. It takes that explanatory variable, in this case 115, we plug it into the equation, and out comes the predicted time to complete the online dissection. So for a student that has an IQ of 115, we would predict somewhere around 20.734 minutes for them to complete the online dissection. Now, notice in this next example, I wrote something over top of it called extrapolation. Extrapolation is trying to make predictions for data that's outside of your data range. So here I tried to input 50. And again, nothing was stopping me from plugging in 50. A student could certainly have an IQ of 50, and I could plug 50 in, and I got a predicted value about 62 minutes. But why is this called extrapolation, and why is this not recommended? Because my data ranged from about IQ scores of 80 to it looks like an IQ score of possibly around 140 there at that high value. So that means that my linear regression model is only good for making predictions inside of that range. That's actually called interpolation. So trying to make a prediction for IQ scores ranging from 80 to 135 would be very smart and very reliable and something that I would certainly trust. Trying to make a prediction for an IQ score outside of that range is not trustworthy, and that's why it's called extrapolation, and it's not recommended. Now, again, notice that there was nothing stopping me from doing it. I plugged 50 in, I got a number, but because 50 was not in the range of my explanatory variables for my data, I would not trust this value. It might not be very trustworthy or a very good estimate. So that's what extrapolation is, trying to make a prediction for something outside of your range. I'll say one more time, you could do it, but it's not recommended. Now, one more thing kids will try to do is they'll try to use their linear regression model to work backwards. They'll take the time to complete an online dissection, and they'll try to plug that in for y hat, and they'll try to solve for the IQ score of that student. You cannot do that. That is not how this equation was created. This equation was created to do one thing and one thing only, which might seem a little bit different from algebra class, but is only created to take an explanatory variable x and give you a predicted value y hat. You cannot take an actual amount of time to do the online dissection, that would be an actual y, not a predicted y, and plug it in for this spot. That spot right there is reserved only for predicted y's, not actual y's. So the equation was created to do that one exact thing. Speaking of how it is created, that's the next step. How do we actually create this linear regression model? Well, to explore that, we have to understand residuals. Residuals are used to determine what makes the perfect line to use for the linear regression model. A residual value is the difference between the actual value and the predicted value of the response variable. In symbols, that's the actual y minus the predicted y hat. It is the vertical distance between an actual point and the prediction from the linear regression model that we would see in a scatter plot. Now, all points have their own residual values. Some are positive if they're above the line, some are negative if they're below the line. But if we add up all of the residuals, they should add up to 0. When all are examined, they should be mixed up. Let's take a look at an actual example to see what residuals look like in a scatter plot. Here we see a scatter plot of the size of several houses in square feet and the price of those houses in thousands of dollars. Now, we've already said that we see a very positive and strong relationship here. As the size of a house goes up, so does its price. But now added in is the linear regression model in red. Now, the residuals, again, are the vertical distances between the predictions from the line and the actual points. Every point has its own residual value, so I can actually draw in these residual values. A lot of them are positive. That means that the actual value is above the prediction. I'm just trying to add in some of them here. And then some of them are also negative, meaning that the actual value is below what is predicted. But what we see here is a bunch of residual values. Now, what makes this red line the best line is that it produces the smallest residuals. It's trying to balance out and make all the residuals as small as possible. Let me just kind of draw a line in for you here that would be a terrible line. If I made this line my linear regression model, we'd all be like, well, that's terrible. It doesn't even go through the data. Well, exactly. Now, it does have positive residuals and it does have negative residuals, but it's clearly not the best because most residuals are really big. For example, even this point right here that looks like it's close to the line would have a huge residual value. So that's the idea, that the residuals are the vertical distances from your predicted line to your actual points. And we want those distances to all be as small as possible, but naturally some are going to be a little bit bigger than others. Now let's talk about calculating actual individual residual values. So for example, one of the houses was 4,850 square feet, and the price of that house was $481,000. How would I find that house's residual? Well, first I have to use the X value, that's the square footage, to get my predicted value. So here is the linear regression model for that line, 74.3534 plus 0.1061x. I'm going to replace the x with my x value, 4,850 square feet, do the simple math to get my predicted value. Now, please note that this is in thousands. So I actually need to move this decimal 1, 2, 3 times. That'd be $589,119. So the actual price of the house was $481,000, but my model predicted it, based on its square footage, to be about $589,000. So the residual is the difference between the actual price and the predicted price. Make sure you get that order correct. I always think actual is first because it starts with an A being the first letter of the alphabet. So the actual minus predicted produces a negative residual. That makes complete sense because the actual price was below what was predicted, and it was negative $108,000 below. Now, a second example here was another one of the houses had an actual square footage of 30,450 square feet, and the price of that house was $561,000. So to find the residual, first I have to use my linear regression model, plug in my square footage to get the predicted price. And here the prediction was only $440,000. Or again, if you want to move that decimal 3 times and be more specific, $440,579. But to get the residual value, I'm going to take the actual price of that house minus the predicted price of that house, and this time I get a positive value. That is because the actual price was higher than the predicted was. So my residual value is $120,000. Now, again, notice these two residuals. One was negative, one was positive. This one right here was a little bit smaller, and all that means is that my predicted price was closer to the actual price, or here it was a little bit bigger because it was a little bit further away, even though it was in the positive direction. So again, calculating residuals individually is really, really simple, but understanding that every single point has a residual value, and we really truly are trying to keep all those residual values as small as possible to produce the best line. A residual plot is actually a scatter plot of our residual values and our x values. In a residual plot, we want to see, well, nothing. We should see no pattern whatsoever. Again, think about why this makes sense. If our line is going through our data, it means that it's going through it. That's going to produce positive and negative residuals in the beginning, positive and negative residuals in the middle, and positive and negative residuals at the end. Because if it's going through the data, there should be some points above the line throughout the graph and some points below the line throughout the graph. Now, some points are naturally going to be a little bit further away, producing larger residuals, and some points are naturally going to be closer, producing smaller residuals. So if we think about the residuals as a collective group, they should be completely mixed up, so a plot of the residuals should show no pattern. Again, positive residuals above 0, negative residuals below 0, and we should see these positive and negative residuals throughout. If you actually see a pattern or a curve in a residual plot, that is an indicator that your original scatter plot was not linear, and a linear regression model should certainly not be used for it. Now that we know a little bit more about residuals, we can understand why residuals help us determine what is the best line for our data. Our linear regression model is known as the least squares regression line because it is the line whose sum of all the squared residuals is the least compared to any other line. In formula, that would look like this. We see that sigma, that's our mathematical symbol for the sum, and we see any individual residual, again, that's the y minus the y hat squared. If we sum up all of the squared residual values, well, we're going to get a number. But we want that sum of the residual squared to be the smallest compared to any other line. That's going to produce the actual best line. Now, why does this make complete sense? To understand that, we can actually take a look at what's called a residual plot. Now that you know what a linear regression model is and what a least squares linear regression model is and why it's truly the best line, the big question is, how do I find this equation? Most kids don't even worry about why it's the best line. They just want the equation given to them. So how do we produce this equation, y hat equals a plus bx? Well, we actually have several different options. One, we actually have some formulas that can be used to actually create the formula. The formulas do require a lot of information, though. We have to have all of our x data. We have to find the mean of our x data and the standard deviation of our x data. Then we have to have all of our y data. We have to have the mean of all the y data and the standard deviation of all the y data, as well as do we need the correlation between the x's and the y's. So to find the y-intercept and to find the slope, we have the following formulas. To find the slope, we take the correlation r times the standard deviation of y divided by the standard deviation of x. And then to find the corresponding y-intercept, we need to take the average y minus the slope that we have to find first times the average x. Now, if I or your teacher or the AP test is ever going to ask you to use these formulas, they will give you all of the information you need to utilize them. You just have to know how to use them. But they're also given to you on the formula sheet for the AP Stats exam as well, so it's pretty simple to use these formulas. But I'll be honest, in most situations, the AP test or your teacher will just give you the linear regression model for you to use free of charge. Or another thing they could do is use what's called a computer regression output model. Think of this as just a way that they could provide you all the information you need to know in order to generate the equation. The least squares regression line has many facts about it that you need to know. The first is the y-intercept. This is the A value. The y-intercept is what we predict the response variable to be when the explanatory variable is 0. Again, it's a y-intercept. That should make sense algebraically. When x equals 0, what do we predict the response variable y to be? Sometimes this value actually makes sense in context of the problem, sometimes it does not, and that's okay. Next up is the slope, and this is the b value. Proper interpretation of the slope hinders upon you understanding that the slope determines how much we predict the response variable to change for every increase of 1 unit of the explanatory variable. I like to look at the slope as a fraction. You could turn any number into a fraction by putting it over 1. So if you take the slope b and you put it over 1, the slope on top is the change of y, the response variable. The 1 in the denominator is the change in x. So the slope tells us for every 1 increase of the x variable, what we predict the change of the y variable to be. Another super important value is the coefficient of determination. Pretty cool name, coefficient of determination. This is literally taking correlation R and simply squaring it. Not too hard to find, correlation squared. Now, what R squared, or the coefficient of determination, tells us is actually super important. It tells us how well these two variables are connected. So it actually gets turned into a percentage. So typically when we have R and we square, we're going to get a decimal, move that decimal point 2 places to turn it into a percentage. And the R squared value tells us the percent of variation in the response variable that is actually explained by the variation in the explanatory variable through the regression model. So I know it's kind of confusing to understand, and most kids just kind of remember like a script, they just write that out. But the idea is this. We have a bunch of different response values, right? A bunch of different y values, and then they vary because they're different. But the R squared value tells us what percent of that variation in the response variables is actually because of the different values for the corresponding x values. So think of it as how strong these values are tied. Obviously, the best you can be is 100%. That means 100% of the variation in y is actually because of the variation in x. But the closer to 100%, the good, right? So 90, 95% is great values. But really, R squared helps us understand how reliable our linear regression model is. Because the more connected the two variables are, the more reliable our predictions are going to be. If your coefficient of determination is only like 40%, that shows that they're not that strongly connected, hence any prediction about the response from the explanatory variable is not going to be as reliable as if it was, say, 99%. The last major value that is needed and asked about is called S, the standard deviation of the residuals. Again, it can be a little bit of a confusing value to understand, but just think of it as this. It is the standard deviation of your residual values. But what it tells us is actually way more important than just knowing what it is. It tells us that when we use our linear regression model to make predictions for y, how typically off those predictions are. So it's basically like an average of your error. Like say, hey, listen, hey, when you use this model, it's never going to be perfect. It's, no predicted value is going to match the actual value perfectly, right? It might be really close, but to be perfect is going to be very rare. There's typically going to be some error, some distance between what is actual and what is predicted for any point. So the standard deviation of the residuals is basically telling you what's the average distance that an actual value is for the predicted value, showing you that when you use your line, how much you're typically off by. Now here you really have to take context into account. So for example, if you're trying to predict the weight of an elephant, right? And your standard deviation of the residuals is 5 pounds. Well, that's actually really, really good. That means that when you're trying to predict the weight of an elephant, you're typically off by 5 pounds when you use your least squares regression line. And when you're trying to predict of an animal that weighs tons and tons, that being off by 5 pounds is really good, reliable predictions. But if you're trying to predict the weight of a rabbit and your standard deviation is 5, standard deviation of your residuals, that is, well, that means you're actually way off because rabbits don't weigh a whole lot. And if you're basically saying, hey, I'm predicting the weight of rabbits, and I'm usually only off by about 5 pounds, well, that's being off by a lot. So you have to make sure that obviously understand that smaller S's are better because that means that typically your actual values are closer to your predicted values, which means you have a very reliable model. But again, you also have to take into account context because 5 might be small when you're talking about elephants, but 5 pounds is certainly not small when you're talking about rabbits. But S is a really cool number that really helps us understand how reliable and how good our line is at making those predictions. Now, we have learned quite a bit of information, and when you're working with a least squares regression model, there is a lot that goes into it. But here's the best part. On the AP exam and hopefully on your unit exam in class, you really are meant to focus on the interpretation of that information. So typically, all the information is given to you in what is called a computer output regression analysis. I know it's kind of confusing, but imagine you have a computer and you dump all of your explanatory variables and all of your response variables into that computer, and beep, boop, 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 beep, beep, it spits out to you everything you need to know in a nice table called a computer regression output table. So here's an example of that for our house problem. When we're taking the size of the house in square feet, we're trying to predict the price of the house in thousands of dollars. This is an example where, again, everything is going to be given to you. So we see a scatter plot, so we could take a look at the overall description of what's going on with our data. We see a residual plot that tells us that our line is a pretty good line, but we also see this computer output table that has in it the slope, the y-intercept, S, and R squared, all the key things that you need to be able to find, use, and interpret. Now, we also see some other numbers in this table. We see SE, stands for standard error, see a t-stat and a p-value. Those are all going to be used way later back in Unit 9. So for right now, you could basically ignore all of those values. Now, in an ultimate problem, you're going to be given all the information you need and ask things like, hey, find the slope and interpret it, find the y-intercept and interpret it, tell me what R squared tells you, and tell me what S tells you. And you can do all of that with one of these computer output tables. All you need to know is what to say and how to say it. And hopefully I've explained that well in this video. Now let's pretend for a second that we were given all of this information together for our house problem. The scatter plot, the residual plot, and the computer regression model. And we could be said, we could be asked, a bunch of different questions. So here it all is. So first we see the scatter plot. That tells us that it's positive, linear, pretty strong. And we see that the bigger the house, the higher the price. In the residual plot, we see nothing, no pattern whatsoever. Again, that's a good thing. It means that our line does a great job of going through the data, producing positive and negative residuals throughout. Now, with the computer output table, we see everything we need. And that very first column, it goes in alphabetical order, A and then B. So our y-intercept is 74.3534. Now, what's the interpretation of that? Well, when a house has 0 square feet, we predict the price to be about $74,000. Now, wait a minute. Just as I mentioned earlier, sometimes the y-intercept doesn't make sense in context, and this would certainly be an example of that. Well, that's extrapolation. Remember that our houses started around 800 square feet, so trying to make a prediction for 0 square feet wouldn't make sense. And if a house had 0 square feet, then it really wouldn't be a house, would it? But that doesn't matter. The interpretation is what it is based on the value. Now, the slope is 0.1061, and of course, we could be asked to interpret what that slope means. Remember, make it a fraction. Put it over top of 1, 0.0161 over 1. This tells me for every 1 square foot that a house is bigger than another house, we would predict the price to increase by 0.1061 thousands of dollars. Now, I realize that that's a weird interpretation because it's in thousands, but basically when you're in thousands, you want to convert, you got to move the decimal 3 times. So that would be about $106. So for every 1 square foot that a house gets bigger, we would predict the price of that house to increase by about $106. Next up, we have the R squared. Remember, we typically turn R squared into a percentage. So it's about 87%. That tells us that 87% of the variation in price of a house is actually explained by the variation in the size of the house. That's a pretty strong connection. 87% shows that these two variables are certainly related, but obviously a lot of other factors besides the size of a house goes into the price of a house. Next up, we have S, that is the standard deviation of the residuals. Here we see it's about $13,000. If you want to be more specific, you could actually move that decimal 3 times and be $13,345. So what that tells us is that when we use this linear regression line to try to predict the price of a house based on its size, we're typically off by about $13,000. And if you're trying to predict the price of a house and you're only off by $13,000, I think you're actually doing pretty good. In this data, houses were very expensive, ranging from $100,000 all the way up to almost $900,000. So for houses well over $100,000 and you're trying to predict the price of them and you're typically only off by $13,000, I think you're doing pretty good. So all of this can come together, and this is what's usually going to be presented to you in an AP Stats type of problem, where you're going to be asked to identify these values and make sure you know how to interpret them. Here's another example, and this might be a good time for you to listen to the example, but then hit pause and try to identify the intercept, the slope, R-squared, and S, and interpret what they mean. Here's the scatter plot of IQ scores versus the time it takes to complete an online dissection in minutes. So here's a computer regression analysis of all of this scatter plot. So again, typical questions could be, what is the intercept, and interpret what it means. The intercept is 93.759. That is, if you have an IQ of 0, we would predict it to take 93 minutes for you to complete the online dissection. Now again, that doesn't make a whole lot of sense because 0 IQ would be really, really, really low. I don't think if anybody has an IQ of 0. But again, it's probably because of extrapolation. It doesn't mean the intercept is wrong. It just means it doesn't have a lot of meaning in context. That typically happens with the y-intercept. Now, what about the slope? The slope is negative 0.635. And well, that tells us that for every 1 point that a person's IQ goes up, we predict it to take 0.635 minutes less for them to finish the online dissection. So as the IQ of a person goes up by 1, we predict it to take 0.635 less minutes to complete the exam, or the online dissection, excuse me. Now, the R-squared value we see here is actually pretty darn weak. It tells us that about 38.6% of the variation in times is actually explained by the variation in IQ. That's a pretty weak connection, showing that they're not very strong. Now, remember, that's R-squared. So what if we wanted to find R to, again, show how weak this relationship is? Well, if you have R-squared and you want to find R, all you got to do is take the square root of it. It's pretty simple math. So the square root of 0.386 is an R value of 0.62. And an R value of 0.62 is fairly on the weaker side. We like it to be, 0.8 or higher to call it strong. So again, it is on the weaker side, but if you look at the data, we do see a lot of scatter in our data. Even though it does have an overall negative linear form, it is still pretty spread out. But again, that just goes to show the fact that our linear regression model is not going to be very reliable because of how low the R-squared value is. Finally, we have S, and S tells us that, hey, when we use this line to try to take an IQ and predict the time to complete the dissection, we're typically going to be off by 11 minutes. And when the values of the times range from, if you look at about 10 to 16 minutes is kind of the overall range of the times, if you're off by 11 minutes and the range is only 10 to 60, that's kind of a lot. But that again makes sense because this data plot does have a lot of scatter to it. And if we were actually to fill in the line of regression, we would actually see that a lot of the residuals are pretty large, which means overall typical values are pretty far off from what we would predict. And that is why we're producing such a large S value. Now, again, that's not necessarily bad. It just means that our line is not going to be the most reliable line when we go ahead to use it. So hopefully this example makes sense and you're starting to understand how we could tie everything together. Don't forget that the other 3 columns, SE, T-value, P-value, are not typically used until Unit 9. So right now we're just going to ignore them. So what are some types of AP questions that could come out of this section that you need to be prepared for? Well, to be honest, kind of all of it. But they really like to focus on, can you interpret values? They love to give you those computer output tables and make sure that you know how to identify the y-intercept and interpret it, identify the slope and interpret it, talk about S, talk about R-squared, know how S and R-squared are truly focusing on how reliable your model is. They like to make sure that you know that a scatter plot should be somewhat linear if you're going to use correlation, and that a residual plot should show no pattern, indicating that a linear model is very appropriate for your data. So it's really more about the interpretation that they like to focus on, not so much in terms of all the teeny tiny calculations. So please be prepared for all of that, just like we practiced in those last two examples. The final section in this unit covers departures from linearity. Now here we're talking about primarily outliers. Outliers are points in your scatter plot that do not fit the overall trend. Typically, they're going to have large residuals, and they're typically going to be either outliers in one direction, like only the X direction or only the Y direction. So let's take a look at an example that has 3 different outliers put into the data so you can see what I'm talking about. Here we see 3 points that I highlighted in yellow, red, and blue, and these are points that I added to our scatter plot for the size and the price of several houses. Let's first talk about this yellow one that is an outlier in the Y direction. Now, why is this point an outlier? Again, it doesn't fit the pattern. It's actually a fairly small house at about 1,800 square feet, which is not an unusually small or big house, because again, it's not an outlier in the X direction, but for that square footage, it has a very high price tag. Maybe it's in a very expensive, like San Francisco or something like that, or even small houses cost a lot of money. Again, it doesn't fit the pattern. For a house of that size, it should have a much lower price. Then we see this point in blue. This is an outlier in the X direction. It is a very large square footage house that has a very average price. So again, it's about maybe about an 8,000 or more square footage house, and it only has a price tag around $300,000. That again doesn't fit the pattern. The pattern should be a house that's really big, should have a much higher price. So again, it's an outlier in the X value. And then we see this red point. Now, I want to make a really important comment here that this red point is actually not an outlier because it is an outlier in both the X and the Y direction. And where you're looking at a scatter plot, outliers are typically outliers in one direction only. Because the red point is an outlier in both the X and the Y, it actually fits the pattern. It doesn't, it doesn't come off the pattern, it fits it. It is a very large house that has a very expensive price tag, which fits exactly what the data should be doing. Now, the other thing I want to note is that outliers in a scatter plot often have big residuals, and you could definitely agree that this yellow point is going to have a huge residual value, this blue point is going to have a huge residual value, and the red point has actually a very small residual value, again showing that when you are a point that's an outlier in both directions, you're technically not an outlier overall for that scatter plot because you fit the pattern. The other thing I want to comment on is if the yellow or blue points were added, it's going to weaken my correlation because I'm adding 2 points that have large residuals that don't fit the pattern. My correlation is going to get weaker. If I remove the yellow and the blue point, my correlation is probably going to get stronger. But that red point is actually going to strengthen my correlation. Adding it extends the pattern. It verifies what I've been saying. Bigger houses have bigger price tags. So that's a good point to add to your data because it extends the pattern and it increases your correlation. One specific type of outlier is called a high leverage point. The high leverage point is a point that is an outlier primarily in the X direction. Now, they're called high leverage points because they actually have leverage to change the linear regression model if we take them away. So imagine if I were to take away a point that has high leverage, again, an outlier in the X direction, that can actually change the linear regression model to move, either move up or move down. This is what we call influential points. Influential points are points that, if removed, substantially change the model. Whether they change the y-intercept, the slope, or the correlation, doesn't really matter, they change the model. Now, points that are outliers in the y direction only don't necessarily have a ton of influence on that linear regression model. It's really those high leverage points, outliers in the x direction, that have the ability to really change the slope of that model. Now, anytime you have an outlier in the y direction or in the x direction, they're going to weaken your correlation. So if you take them away, they're going to strengthen your correlation. Add them in, they're going to weaken your correlation. Hopefully that makes sense to you. But a high leverage points are the most concerning because they really do change the slope of that linear regression model. Here's a great example that will help you understand how an influential point changes the slope of the line. So here we see a point in purple that is clearly a high leverage point. It's an outline in the X direction. Its Y value is kind of actually right in the middle. Now, because this point is an outline in the X direction, it actually has the power to influence the line and pull the line closer to it. Remember, that least squares regression line is trying to keep all the residuals as small as possible. It doesn't really want to have any big residuals, so oftentimes it will actually move closer to that high leverage point, trying to make it have a smaller residual. But in turn, that actually means the line actually doesn't fit the data very well. If I were to take away that point, if I were to get rid of this point, we would actually see that the best line would be a line maybe going through the data like this. So again, adding that point changes the slope, which also simultaneously means if I remove that point, it's going to change the slope. So again, these are all signs of influential points. They're outliers in the X direction more so than the Y. They actually appear to have a smaller residual because the line is so influenced by it, trying to give it a small residual. But if it's removed, the slope changes significantly. This is what we see as an influential point. Well, that's it for Unit 2. Hopefully you learned a lot, hopefully you remember a lot, and hopefully it was a really nice, fairly simple review that covers all the major things that you need to know, whether you're looking at 2 categorical variables or 2 quantitative variables. That's basically what this unit comes down to, is those 2 topics: categorical variables, relationships between them, using a 2-way table and segmented bar graphs, and scatter plots, analyzing the relationship between 2 quantitative variables. But keep in mind, I want to say this one more time to end this video. Even if you see a real, strong, great association between 2 variables, whether they be categorical or whether they be quantitative, that does not mean necessarily that causation is implied. Just because one variable is related to another does not mean that one variable causes another. Please keep that in mind. All right, hopefully you liked the video. Please make sure you check out my ultimate review packet. You can get to that website using the link in the description. It's got access to the study guide, the answer keys, multiple choice practice, free response practice, and much, much more. Enjoy. I'll see you later.